Dimension, one of my favorite topics in the whole course. So the idea here is that we've built up enough theory to start to harvest lots of benefits. And dimension is sort of one number you can use to describe how complicated a vector space is. So let's see the definition here. So here's a remarkable theorem. Remember what we said about bases. One vector space can have infinitely many different bases, but here's something that all of those bases have in common. Every basis of a vector space has the same number of vectors. So here we have an example where I've constructed a vector space V as the span of 1, -3, 5 and -2, 8, 1. And then I went home and I found different bases. Another basis is -4, 14, -9, and 3, -11, 4. And yet another basis is -5, 19, -3, and -3, 11, -4. These are three different bases for the same vector space. But what the theorem says is that all of these bases have the same number of vectors. So each one of these bases has exactly 2 vectors. This is the concept of dimension. This number of vectors is called the dimension of the vector space. So in every one of these bases, we have 2 vectors. So what we would say here is that this vector space has dimension 2. And we write this as dim of v equals 2 here. So if you want to calculate the dimension of your vector space, you need to find a basis, any basis, and then count the number of vectors in the basis. So here we have an example where I've row reduced a matrix A, and I've found that I have 3 pivots in the reduced row echelon form. One of the things we said in the last lecture was that we can find a basis for the column space by looking at the pivot columns of the original matrix. Here we have 3 of them. So we have found a basis of the column space. The column space of our matrix is the span of the 3 pivot columns. Now, what do we know? There are infinitely other bases out there, but every single one of those bases will have the same number of vectors, and that number of vectors is 3. So we found a basis for our space, we've counted the number of vectors, here it's 3. So what we conclude is that the dimension of the column space here is equal to 3. It's critically important that we understand that this concept of dimension is intimately tied to this concept of basis. It's not the number of coordinates that we're interested in here. Every vector in the column space will have 4 coordinates. However, the idea is that we're using 3 linearly independent vectors to reach every vector in the column space here with linear combinations. So the dimension here is 3, not 4. What else can we do here? So keep in mind, Rn itself is a vector space, and every vector in Rn is a linear combination of the columns of the n by n identity matrix. So the way we might write this is that Rn is the span of the n columns of the n by n identity matrix. Very common notation for these columns is E1, E2, up to En. And what the consequence of this is, well, those columns are linearly independent. They're the columns of the identity matrix, and there's n of them. So this is the proof, so to say, that the dimension of Rn itself as a vector space is n. These vectors are important, so we can give them a name. These are often referred to as the standard basis vectors of Rn. Now, how should we think of dimension? What is dimension doing for us? I like to think of dimension as a concrete measurement of how complicated a vector space is. Think about the least complicated possible vector space. Remember that the only vector that's required to be in any vector space is the 0 vector. So let's say that we have a vector space where the only vector is the 0 vector. Well, in this case, there are no vectors we could use to construct a basis. So every basis, if you want to think of it, has 0 vectors in it. That's the 0-dimensional vector space. What's the next level of complexity? Well, the next level of complexity is if I just have one vector in any basis. What this would mean is that my vector space just consists of all multiples of this one vector. So the vector space would look like a line in space. This is the situation where the dimension of our vector space is equal to 1. So this is sort of like the second least complicated possible vector space. Something that just looks like a line in space. What about if I have two basis vectors? If I have two basis vectors, the idea is that if I take all linear combinations of these vectors, I end up generating what looks like an infinite two-dimensional plane that lives in space. And this is what a generic two-dimensional vector space looks like. So, and then the idea proceeds from here. Dimension 3 would look like some sort of infinite three-dimensional like solid cube. Dimension 4 would be whatever the four-dimensional analogy of that is, so on and so forth. So as the dimension grows, I like to think of the vector space as more and more complicated. Keep in mind, in our first example here, the idea is that the only zero-dimensional vector space is the space that's spanned by the zero vector. So the only vector in that space is the zero vector. Okay, so I want to conclude this first little segment by just mentioning a few important properties of bases. So let's say that we have a list of vectors in a vector space, v1, v2, up to vk. One thing we know about dimension is that if this number k here, which is the number of vectors in the list, is greater than the dimension of the vector space, I automatically know without having to do any calculation that the list of vectors I'm dealing with is linearly dependent. So if I'm working inside of a three-dimensional space and you give me 4 vectors, I don't have to do any calculation. I know those 4 vectors are linearly dependent. And here's a second useful theorem. Remember, if you want to check that a list is a basis, you need to check both of the axioms, the spanning axiom and the linear independence axiom. But if you know the dimension of your space beforehand, it turns out that you only need to check one of the 2 axioms. So if you know the dimension is D, well, what that means is that any basis has D vectors. So if you want to check whether or not a list of D vectors is a basis, you could check that the span equals V, and that automatically tells you that the linear independence axiom works. On the other hand, if you have the right number of vectors, you could just check the linear independence axiom, and that immediately tells you that the spanning axiom works. So if you know the dimension, and you want to check whether or not a list of vectors is a basis, this theorem is saying, well, you can cut your work in half, which is definitely useful.